Today, we're going to start our chapter on friction. And I know you've all seen friction before in physics. Specifically, we're talking about dry friction between two dry materials. So no water, no oil, no lubrication at all, just dry surfaces. And here's the picture. We have an object of some kind. It could be a book or a brick. If you're pushing on it with a force P, it might start sliding, it might not. It really just depends on how much friction there is. So we're talking about friction that specifically occurs at some kind of an interface. And when we talk about this in this class, since this is a statics class, we're primarily going to be concerned with what's called the static friction coefficient. We use a Greek letter mu and usually a subscript S to mean static. There's also another friction coefficient called the kinetic friction coefficient that you're going to see when you get to dynamics next semester. That we usually use the Greek letter mu as well with the subscript K for it. And here's the idea is that if I apply a applied load of some kind here, if I were to plot how that friction force varies as I increase the value of P, the applied load, well, if I don't apply any force to this object at all, if P is 0, there is no friction force pushing back in the other direction. And so we start out at 0, 0, no applied load, no friction force. And then as we increase the load P, moving to the right here, the friction force goes up, and it's a perfectly linear, like on a 45-degree angle here, because if I apply a P of 10 pounds, I'm going to get a friction force of 10 pounds. Because let's draw a quick free body diagram. Here's my object. I'm pushing with a force P. The friction force is going to oppose that motion in the other direction. And I have a weight acting here, and also at that surface, the ground is pushing up with what we call a normal force. But if I sum forces in the x direction, what I'll find is that P and friction force are exactly equal to each other. So if you apply 10 pounds of force, you get 10 pounds of friction, 20 pounds, etc. But then what's going to happen is there is a maximum value that we're going to reach right here. Call this, F friction max or whatever. And then once you exceed the max amount of friction that is available between your two surfaces, and this is a function of the surface roughness, it's a function of the specific materials that you're talking about. So static friction coefficients are going to be different numbers. When you reach the most friction that is available at this surface, what's going to happen is it's going to start sliding because you can't have any more friction. And once you start sliding, we actually observe a little bit of a drop in the friction force. So this is at the point where motion impends, it's just about to start sliding. You'll have your max friction. If you push any harder at all, it's going to start sliding. And once it starts sliding, the friction force actually drops a little bit because this kinetic friction coefficient is a little bit smaller than the static friction coefficient. And the idea there is that those surfaces aren't perfect. You have little waves and bumps and things, surface roughness. And so when they're sitting there stationary, the object tends to kind of settle down into the grooves. Once you start pushing it, to do that, you have to put a little more force to overcome that, but to keep it moving requires less to get it started moving. Static friction is just a little bigger than kinetic. That's all we're going to say about kinetic friction in this class, this semester. You will spend more time with that in dynamics next semester. Now, how do we use that friction coefficient? Well, you've seen this equation before in physics. We have the big governing friction equation, which tells us how to know what that max friction force is. So what it says is that the force of static friction, always will be less than or equal to the coefficient of static friction times the normal between the two. If you push down harder on this object, you'll increase the normal force, which increases the available friction. If you have less normal force, you'll have less friction available. But the friction force can always be less than that. This is not maybe we shouldn't call it an equation. How would we call it? The friction inequality, because friction is only equal to coefficient of normal right when it's about to slide. But in general, friction is all we know is it's got to be less than or equal to that. So we'll replace this with a friction equation equals coefficient static friction times normal only when motion is about to happen. We say when motion impends. So when the block is about to start sliding, or we want to know what's the maximum friction available, that's when we use the friction equation. The rest of the time, we're going to use this as an inequality. On our free body diagram we just drew, the motion was about to act to the right. Motion impends to the right because I'm pushing to the right. So that means that the friction acts to the left. Friction never gives you like help. Friction is always trying to prevent you from sliding. So if you're trying to push it right, the friction have to oppose that and act to the left. Here's going to be our solution strategy with all of our friction problems, every single one of them. Our first step is going to be to draw a free body diagram. And when you're doing that, try to guess the correct direction for friction. Now, in the vast majority of problems that you'll ever encounter, if you happen to guess wrong, you will just get a negative sign and nothing bad will happen. But there are a few kind of interesting friction problems where if you guess the wrong direction, you will actually get the wrong answer. And I can actually give a really quick example of that. If we have an incline and we have an object sitting on the incline and we are trying to solve for the force required P to just start moving up the incline, depending on the set of conditions, if the incline is really steep, if this angle is really steep, it could be that there are actually two solutions to the problem. There's the P that will just start to get it moving up the hill. That's one P. There's also a P that would be required to just prevent it from starting to slide down the hill. If it's steep enough that it would start sliding downhill without you needing to apply any force at all, there could be two solutions. So if you're trying to specifically solve for the force P to get it start to move uphill and you draw the friction in the wrong direction, you would be getting the other solution, the P to prevent it from sliding downhill. So that's the quick example I can think of where guessing the wrong direction for friction could give you the other solution instead of the solution you're actually looking for. So we do want to try to guess the correct direction for friction. The other thing I want to mention about free body diagrams before we go to our next step is I do want you to keep N and friction force, the normal force and the friction force, as separate unknowns on your free body diagram. I've seen a lot of students that because you have this friction equation drilled into your head from physics, oftentimes want to just replace friction with this on their diagram. Don't do that because this is not always true. This is only true in motion and pens. So I want you to draw friction on there as the force parallel to the surface, N on there as the force perpendicular to the surface. The other mistake I see a lot of students make is they want to try to replace N with the weight. Don't do that. Normal force is sometimes equal to the weight, but sometimes not. So just draw them as totally separate unknowns on your free body diagram and then solve for them. So that's our second step is going to be to write our good old friendly equilibrium equations. We're going to be summing forces equals 0 and possibly summing moments equals 0. Usually with friction problems, we need a third step. What we typically want to do in our third step is either check when we're done that your friction force needed is less than the coefficient times the normal, because if it's not, it means that the problem actually is not in static equilibrium and actually would have started sliding. So we're going to solve the problem and make sure that there was enough friction. Or if motion impends, and oftentimes the way that they tell you motion is going to depend is they want to find the biggest force before motion happens or the smallest force required to start motion happening. Those are examples of the wording you'll see for impending motion problems. If motion impends, we will also use that the friction force is equal to the coefficient times the normal. In this equilibrium equation step, we may not have enough equations to solve because if it's a motion impending problem, we may need to add this as third or fourth equation with these others to be able to solve. So you're either in a friction problem going to be just double checking that it didn't slip or using the fact that you're right on the verge of slipping to add one more equation to be able to solve. All right, it's example time. We start with an easy, then maybe a medium difficulty, and then a really hard example. So we have this ladder, tells us it weighs 80 pounds. The words uniform weight mean that we're going to apply that force at the middle of the ladder. And they tell us that the wall at B is smooth. What that means is that whatever the friction is at the wall, it's small enough we're going to neglect it. I don't know if it really is. Bricks are usually kind of rough, so it might not be a great idea. But you will find this in some of these textbook problems where in order to have the problem be solvable using statics equations alone, in order for it to be statically determinate, we sometimes need to assume frictionless at certain phases so that we have enough equations to solve for everything. And then they tell us the coefficient of friction at A is 0.4. That's down here at the bottom. And they're telling us the angle theta is 60. So we're supposed to figure out just will it slip? So this is a problem where we're going to not use our friction equation to calculate anything. We're simply going to use the friction inequality to confirm whether it will or will not slip. First step is a free body diagram of that ladder. So there's the side view of my ladder. The weight is going to act in the middle because it's a uniform ladder. We just got the weight of the ladder. B is smooth. That means free to slide along it, but we need to apply a perpendicular force, and we call that perpendicular force a normal force at B. Then at A, we've got a surface with friction, so we will still have a perpendicular force that we call normal, and a tangential or parallel force to the surface that we call friction. And again, trying to guess which way this is going to rotate, I think if this were to start moving, it would move so that this goes down and that goes down and this goes out. So you're kind of rotating this way. You guys have seen a ladder or something that slips. This end is not going to slip in toward the wall. This end is going to slide out away from the wall. Friction has to oppose that outward motion. So the friction force at A has got to act to the right to oppose the motion. And that's everything for the free body diagram. We've only got 3 unknowns on here, so we should be able to solve for all 3. Equilibrium equations, that's our second step. If we sum forces in the y direction, I can actually solve for something right away. I've got NA is upward, minus 80 pounds is equal to 0. So NA is equal to 80 pounds. If I sum force in the x direction, I've got 2 unknowns, so why don't we sum moments about point A next? So summing moments about point A in a counterclockwise direction, I will have NB, and I need that perpendicular distance. So it's all the way up here. Perpendicular distance would be that height. The ladder is 15 feet long and the angle is 60 degrees. So this side right here, this perpendicular distance would be, it's the side that's opposite the 60 degrees. So this one's going to be times 15 feet. Opposite 60 means sine of 60 degrees. That's the first part of the moment. I'm going to move this so I have more space. The other moment is going to be clockwise, caused by the 80-pound force. So we'll have minus 80 pounds, and the distance away looks like it's only 7.5 feet up, because it's halfway up. We're going to use this little triangle. Since the force is acting downward, the perpendicular distance is on the side that's adjacent to the 60 degrees. So my distance here will be 7.5 feet times the cosine of 60 degrees. That all has to sum to 0. And solving, we get that the normal force at B has to be 23.1 pounds. Then if we sum forces in the x direction, we get the force of friction at A minus the normal force at B equals 0. So the friction force at A is also 23.1 pounds. So we've solved for all of the unknowns on our free body diagram. Now we need to check friction inequality. So let's figure out the maximum amount of friction available is going to be the coefficient of static friction times the normal force at A. So we're going to grab the coefficient of friction was 0.4, and the normal force at A we calculated, which is 80 pounds. Multiply that out, and we get that the max friction available with this setup is 32 pounds. That's great, because the friction we need to keep the ladder from slipping is less than that. So since the force of friction at A is less than F max, it does not slip. And we're done. I said that was the easy warm-up example. Here's the harder example. So we've got a guy that is trying to push a dresser, and they tell us the dresser has a weight of 90 pounds and rests on a floor with a coefficient of friction between the dresser and the floor, right? I think I forgot to mention, coefficients of friction aren't just based on the material of one surface. They're based on the 2 different materials in combination. So wooden dresser on tile floor has one coefficient of friction. In just a minute, we're going to maybe look at the friction between his shoes on the floor. That might be a totally different coefficient of friction. So it depends on the 2 materials and their condition, what the friction is going to be. So we're starting with a dresser, 90 pounds, and we know the friction between the dresser and the tile. This man is trying to move it by pushing down and to the right with a force F. We're told that theta is 30 degrees. And the first question is, what is the smallest force he needs to push to get the dresser started moving? So that is a motion impending kind of language, right? Determine the smallest magnitude of force F needed to move the dresser. So we're going to solve for F right at the condition when the dresser is just starting to move. Then part 2 of the problem, we find out the weight of the man, and we're supposed to figure out how much friction do we need between his shoes on the floor so that he doesn't slip trying to move this dresser. So I do want you to think of this as kind of two totally separate problems. We're going to first figure out the force to push the dresser using a free body diagram of the dresser. Then we're going to go do a diagram of the man to figure out the required friction coefficient between his shoes and the floor. Start with the dresser. At its heart, though, this is really like one of those frame and machine problems that we spent the last couple of weeks solving. We've got two things contacting each other. We're going to draw diagrams of them separately and see if we can solve the problem. So here is my dresser. What all is acting on it? It has got a downward weight of 90 pounds, and somebody is pushing on it with a force F at a 30-degree angle, and we do not know F. Now I've removed the floor to draw this free body diagram. So what does the floor do to the dresser? It applies a force to the dresser. We don't know the magnitude of the force. We don't know the direction of the force. So when we don't know either the magnitude or direction, we're going to draw a force in two directions, two perpendicular directions. And we usually like to draw them perpendicular to and parallel to the surface. And we call the one perpendicular the normal force. And then the other component that we don't know is the friction force. We want to draw that parallel. It should oppose motion. So since he's trying to push this thing over to the right, the friction has to go toward the left. So there is our friction force at D. This is just like if you removed a pin from something, you're going to draw, say the pin was at A, you're going to draw AX and AY on there. Well, now we're just going to give them different names. We're going to call them normal and friction force. And then we'll use what we know about friction to get us an additional equation if needed. So we're still just drawing two unknown forces. We're just calling them normal and friction. That is our whole free body diagram. Now you might notice I do not know how wide the dresser is or how tall the dresser is. As a result, I cannot sum moments. We will sum moments in the next couple of classes when we start to try to figure out if things might tip over before they slide. But until you have dimensions, you can't sum moments. So all we can do is some forces in the X and some forces in the Y. But you'll notice we do have three unknowns. So we will need a third equation to solve, and that's going to come from the fact that motion impends. The smallest magnitude of F is code for motion impends. And that means we can use our friction equation. So we have a free body diagram. Let's write our equilibrium equations. Only summing forces because we don't have any distances to sum moments. So as I sum forces in the X direction, I will get that F cosine 30 degrees minus the force of friction at D is 0. And if I sum forces in the Y direction, I get that minus F sine 30 degrees minus 90 plus ND equals 0. So I have two equations, not enough to solve, right? So I need a third equation. So we're going to use our friction equation, only using it because they told us we're trying to solve for the point when it's going to start sliding. Friction equation tells us that the force of friction at D is equal to the coefficient of static friction at D times the normal force at D, which is 0.25 ND. Three great equations. Easiest way to solve, usually to replace the friction with coefficient times normal. And then we would have two equations with just F and normal force at D in them, and we can solve for normal force at D. Solving, we get the normal force at D comes out to be 105.1 pounds. And then the force that you had to apply to it comes out to be 30.4 pounds. So we solved the first part of the problem. I do want to point out to you guys, normal force at D is definitely not equal to the weight of the dresser. So if you had just replaced ND with 90 pounds, you would get the wrong answer here. The normal force is bigger than the weight because of the downward component of the force that he's pushing on it with. So that actually does increase the friction. So anybody that's ever moved a dresser knows you do not want to be pushing down on it to move it, because pushing down on it increases the normal force, which increases the friction force, which increases how hard you have to push. You would be better off just pushing straight horizontally instead of downward. But it makes for a good example because I can show you guys that the normal force is not always equal to the weight. So we did the first part. We found out how hard he has to push. Next question is, how much friction does he need between his shoes and the floor so that he himself can actually apply that force without slipping? So to do that, we need a free body diagram of the man. So for the free body diagram of the man, has a downward weight of 150 pounds. Then he is pushing down on the dresser, down and to the right, with a force of 30.4 pounds. That means the dresser is pushing back up to the left on him with 30.4 pounds at that same 30-degree angle. We tend to sometimes forget that a person pushing on a thing is just like two bars pushing on each other. So just like with frames and machines, if we draw a down and to the right force here, we have to have an equal and opposite up and to the left force on the other thing that's contacting the dresser. And then at the ground, we're going to end up with a normal force on the man. And let's see, the dresser would tend to push him back that way. So the friction force on him has to oppose that motion and act to the right. Force of friction on the man acts to the right. There's the free body diagram of the man. We have two unknowns. We can solve for both of them. So if I sum forces on the x, I've got minus 30.4 pounds times the cosine of 30 plus the force of friction on the man equals 0. So we get that the force of friction on the man is 26.3 pounds. Then if we sum force in the y direction, we've got the normal force on the man minus his weight, 150 pounds, plus 30.4 pounds times the sine of 30 equals 0. So the normal force on the man is actually less than his weight. It's 134.82 pounds. All right, we got the friction force on the man, we got the normal force on the man. The problem asks for the coefficient of friction so that he just barely doesn't start slipping. What's the minimum coefficient of friction? So it's another motion and pen problem. So we're going to use that the friction force on the man is equal to the coefficient of static friction times the normal force on the man. So coefficient of static friction is going to be that friction force that we need divided by the normal force that we have. It comes out to be 0.195. And I remember the first time I was solving this problem, I solved it, we got the number, and I said to my students, does that sound high or low? Think he can do it? Would it be okay if he was wearing socks, or does he need to be wearing shoes? And we didn't know. So I actually brought a bunch of materials into class and we tested every shoe in my closet and a bunch of different kinds of socks. And everything I tested, I put it on tile and hardwood floor. Everything I tested gives you a friction coefficient that is bigger than this. It doesn't matter what are on your feet, you will have plenty of friction. You're not going to slip when you're pushing with just 30 pounds of force at this angle. Let's do our third problem, which I told you is the hardest. There are three things that make this problem challenging. The first is that it has two components pinned together. So we have to do our frame or machine analysis. We can't just do this with one object. Second thing that makes it hard is we have something round. And friction for round things is just so much harder than friction on blocks and rectangles. The third thing that makes it difficult is that it is sitting on an incline instead of sitting on a horizontal surface. What are we going to try to solve for though here? We've got a disc with a mass of 35 kilograms. So we'll need to convert that into newtons to get the weight of it. We know the friction coefficient at the surface is 0.2. That's where it contacts the surface at C. And we're supposed to solve for P, the biggest P you can apply before the disc starts to slip. And it asks us to just neglect the mass of the bar. It wouldn't be much harder if we added the mass of the bar, but we're going to neglect it because it must be small compared to the disc. With machine frame type problems, as you've discovered, it's often better to just draw the separate free body diagrams to start with, since the whole ones are sometimes really complicated. So if I start with a free body diagram of the bar, that's the easy thing to draw the diagram of. Let's start with the easy thing. It has no friction, it's a rectangle. We have an applied force P that we don't know. B is a pinned support, so we're going to have a BX and a BY in two directions that I do not know. And then at A, we have two parts pinned together. So I'm going to need an AX and an AY. I don't know what direction they're in, but I'll guess. And then when I draw them on the other part, I'll have to flip their direction because they're two things that interact with each other. So we need equal and opposite pairs. And there's nothing wrong with my free body diagram, but it does have 5 unknowns. I'm going to go ahead and draw the other free body diagram and then we'll talk strategy. It's a circle and acting at the middle is the weight, mg. And at A, we already know at A, we're going to have a leftward AX and a downward AY because they have to be equal and opposite to the AX and AY that we drew before. And now we have that incline. What I find helpful with the incline is to actually draw it on here. And I like to make it a fairly exaggerated angle. So you do not want to make your angle look like it is 45 degrees. So there's my angle. I'm not drawing the surface on here. I just want to have the angle there as a reference. Now, it's a surface that I've removed, and so it's going to prevent motion both perpendicular and parallel to the surface, and I want to draw those as the perpendicular force I'm going to call the normal force at C, And then the parallel force I'm called the friction force. That friction force, I do want to try to figure out which way it's going to act. So looking at the overall problem, since somebody is pushing down here and B can't move, it can rotate about B, but it can't move. So pushing P down is going to cause A to move downward. Well, if point A on this disk moves downward, can you see that this is going to have to start rotating in a clockwise fashion? So the only way for this to move downward is if it rotates clockwise. Because A is going to make it rotate clockwise, we need the friction force to oppose that motion. So I'm going to draw my friction force in that direction. If you can't figure that out, not a problem. This is an example where it won't matter which way you draw the friction force, you'll still get the right answer. It will just come out as negative if you draw it the other way. Okay. So again, the idea is that in order for A to move downward, this has got to rotate clockwise. Friction wants to oppose that by causing a counterclockwise rotation, which would mean it needs to point that direction. All right, it's another diagram. It only has 4 unknowns actually, which is good news. But here's the problem is this is the diagram that has P on it, and this is the diagram that has friction on it. And I'd really like to get information about P over onto this diagram as efficiently as possible. And I think the way to do that is use this diagram. If we sum moments about point B, I'll be able to get a relationship between P and AY. Can you see that? If I sum moments about point B, BX and BY won't be in that equation, and AX is directed right at B and won't be in the equation either. So I'll get a nice simple equation that relates P and AY. So then I'll be able to replace AY over here with something in terms of P, and that'll let me proceed with solving for how big of a P will cause it to be about to slip. So over here, I'm going to sum moments about B. And in doing that, I've got P will cause a counterclockwise moment, and it is 600 millimeters away. If you want to call it 0.6 meters, you can. And then the other direction, I've got AY causing a clockwise moment about B, and it is 900 millimeters away. Won't matter if you use 600 and 900 millimeters or 0.6 and 0.9 meters. As long as you're consistent, those units are going to cancel out anyway, and you simply get that AY is 2/3 of P. And it turns out we don't need to do anything else with this diagram, because if you sum forces in the X, all it's going to do is solve for BX. And if you sum forces in the Y, it's just going to help you solve for BY. And I don't think we actually are going to need those, because now I can put information about P directly on this other diagram, and I think we can solve the rest of the problem using this diagram alone, which doesn't have BX or BY on it. Done with the blue diagram. On the purple diagram, we're going to say AY is equal to 2/3 P and just use that going forward. So now using this disk diagram, I told you that circles are hard and inclined angles are a little bit hard too. The difficulty with a circle is figuring out where to sum moments. If you make a really good choice of where you sum moments with a circle problem, they're usually really easy. If you don't, you can end up with some kind of nasty math. Here are the places that are good candidates for summing moments. You could sum moments about point A. A is good because AX and AY go right through it. However, I don't know the perpendicular distance from the force of friction to point A, and the normal force to point A, I have no idea how to find that perpendicular distance either. It looks really complicated, and once you have circles involved, finding distances is really not fun. The other place that might be tempting to sum moments would be point C. Nice idea, because then NC and the force of friction of C don't contribute to the moment. But again, then I got to figure out, well, how far is my weight from that point? I don't know. It's a weird number. I got to calculate it. How far is AX from that point? That point is not down here on the bottom of the circle where it would just be a radius away. It's partway up the side of the circle, 30 degrees. So if you sum moments about either A or C, you've got a lot of really difficult distances to find. So often with a circle, first consider summing moments about the middle of the circle, point O. And here's why. So first of all, the weight will not cause a moment because it goes right through the center of the circle. In this problem, AX won't cause a moment because it's pointed straight at the middle of the circle. And finally, NC, the normal force on it anywhere around the perimeter of a circle, is always directed right toward the middle of the circle. And because it's directed right toward the middle of the circle, it doesn't cause a moment. So the only forces that cause a moment about point O are AY, which will cause a clockwise moment, and FC, which will cause a counterclockwise moment. And here's the beauty. Their distance away is just the radius of the disk. So this becomes a very easy moment equation to write. We will have counterclockwise, the force of friction at C times the radius of the disk, 200 millimeters, minus AY times the radius of the disk, 200 millimeters. Look how easy that was. Oh, and we're going to actually replace AY with 2/3 of P. The force of friction at C is equal to 2/3 P. That is a really nice result that's really fast to get. And it comes because we chose very well where to some moments. I encourage whenever you have a circle problem, try summing moments about the middle of the disc or the circle. Now we need some forces in the X and Y direction, some forces in the X direction, and I just chose to use the right direction for X, and for the Y, I chose to use up. You can sometimes with inclined plane problems make a case for summing forces along the incline and perpendicular to it, but because we've also got a force in the X and the Y direction over here, it doesn't really save you much to choose to do this as your X and Y direction. So I just picked the regular old X and Y direction. So my X force equation ends up being minus AX. And then I'm going to have plus a component of friction force. Well, this friction force is along the 30-degree angle. There's the 30 degrees. So parallel to the x-axis is adjacent to the 30. So I'm going to have plus the friction force at C times the cosine of 30 degrees. Now, here's where inclined planes get a little bit tricky. We know that this friction force is 30 degrees from the horizontal. We need to figure out the orientation of the normal force. It's perpendicular to the friction force. And so one way you can get the angle is to say, well, because it's perpendicular, if the friction force was 30 from the horizontal, the normal force is 30 from the vertical. And if you've drawn your angle exaggeratedly, it's pretty easy to see that in this triangle, that is definitely the little angle, the 30-degree one. So for the X component, the component of NC in the X direction is pointing to the right, and it's the side that's opposite the 30-degree angle. So I'm going to end up with a plus NC sine 30 degrees equals 0. Here's a great check on if you did the angles right. If you used cosine of 30 for your friction, you need to use sine of 30 for your normal in a single equation like this. If you ended up with cosine and cosine, you would know you had done the angles wrong. Y force equation, I'm going to have minus AY, which is 2/3 P, minus mg. The friction force is directed downhill, horizontal and vertical component. The vertical component is opposite the 30-degree angle. So we end up with minus force of friction at C times the sine of 30. And then the normal force is pointed upward. The upward component of the normal force is adjacent to the 30. So we'll end up with plus NC cosine 30 equals 0. So another way to double check these is, just like always, if you used cosine in the X for the friction force, you'll use sine for the Y forces with the friction force. If you use sine for the X for the normal force, you'll use cosine for the Y for the normal force. We've done our equilibrium equations. I want to simplify them as much as possible, and then we'll see where we're going to go from here. I know that AY is 2/3 P, so I can replace that right there with 2/3 P. And I know that the friction force is 2/3 P, so I can replace that with 2/3 P there and there. I've got minus AX plus 2/3 P cosine 30 plus NC sine 30 equals 0. Then the other equation, I've got minus 2/3 P minus mg minus 2/3 P again times sine of 30 plus NC cosine 30. When I look at that, I've got two equations with three unknowns. I've got P, AX, and NC in there. So now they were asking for us to solve for P when the disk is just about to slip, right? Maximum vertical force P without causing the disk to slip. That means we're solving when motion impends. The idea being that if you applied just a tiny bit more P, it would slip. So we're going to use our friction equation. It says that the force of friction at C is equal to the coefficient. What was the coefficient? 0.2 times NC. And what I figured out works really well to solve this problem is you can actually solve it just using this single equation right here. If we simply replace or get rid of the NC by replacing it with friction force divided by 0.2. So doing that, let's rearrange this. So that means that NC is the force of friction at C divided by 0.2, but the force of friction at C was 2/3 P divided by 0.2. So if you plug that in for NC, you have one equation with P in it. It looks like this. So we got minus 2/3 P minus, it was 35 kilograms times 9.81 meters per second squared, minus 2/3 P sine 30 plus it's 2/3 P divided by 0.2 times the cosine of 30 degrees equals 0. Solving, we get P, and P comes out to be 182 newtons. And we're done. So I mentioned the 3 things that made this problem hard. First is it has multiple things pinned together. Strategy is break them apart and remember, like we do with frames and machines, to do equal and opposite pairs where they contact each other. Second thing that made this hard was the round thing. So my hint with a round thing is think very carefully about where you sum moments. If it's a round thing with an incline in particular, you probably want to sum moments about the middle of the disk because all of your normal forces point right at the middle and you'll get a simpler equation that just has stuff like the friction forces in it. Third thing that makes it hard is the incline. And a couple of tips for inclines is, first of all, draw your incline with an exaggerated angle. Don't make it look like 45 degrees because with 45 degrees, it becomes really hard to visualize which angle is which. So draw it so that it looks pretty obviously like that is a small little angle. And that way, when you draw your friction force along the incline and your normal force perpendicular, it will help you see that since the incline is 30 from the horizontal, the normal force has to be 30 from the vertical. The other tip for that is in your equations, if you're summing forces in the x, for example, you should have a cosine next to your friction and a sine next to your normal. Or if you have a sine next to your friction, you have a cosine next to your normal. You should never have the same trig function next to both of them. Okay, that's it for day 1 of friction. We got a couple more classes where we will keep practicing some problems get a little bit more difficult. Like I mentioned, we'll have multiple objects in contact. Sometimes you have to try to figure out which surface is going to slip first. And then we will also move into solving problems where you might need to check if something might tip rather than slipping.